Welcome to Lecture Online, and today we're going to talk about something new regarding electromagnetic induction, and that is Lenz's law. Now, before we talked about Faraday's law already, and let's review what that means. Faraday's law states that an EMF is induced, like a voltage is induced around a current carrying loop, a loop that is able to carry current like a conductor, if the flux through the loop changes. So if the flux increases or decreases, an EMF will be induced. If the flux increases, then an EMF will be induced carrying a current in one direction. If the flux decreases, then an EMF is induced that will carry the current in the opposite direction. Now, you may have wondered why that negative sign is in that equation. Well, the negative sign is there to help us understand Lenz's law, the second aspect of that. What we didn't learn yet is what is the direction of that current in the loop when an EMF is induced. Well, Lenz's law helps us understand that. Lenz's law, paraphrased a little bit by me, states that the induced current, which is caused by the induced EMF, so an induced EMF will induce a current. So Lenz says the induced current produces a magnetic field of its own, because anytime you have a current going around a loop, there will be a magnetic field through the loop. That magnetic field is caused by this induced current, and that magnetic field opposes the change in the flux that caused the induced current in the first place. So let's repeat that. We have a changing flux through a loop that produces an EMF. That EMF produces a current. That current, which is induced by the induced EMF, will produce its own magnetic field, which that magnetic field will oppose the change in the flux that caused the induced EMF and the induced current in the first place. Wow. That's really a handful, isn't it? Or a mouthful, if you want to call it that. So, to help you understand that, I've come up with some examples here, very standard examples you'll find in any textbook, where we can try to figure out how to do that. So, here I have a magnet that has a north and a south, and the north end of the magnet is plunged towards a current carrying loop, or a loop that can carry a current. Now, understand that the magnetic field lines of a magnet with the north facing down will be downward, and you can see that as this magnet is brought closer and closer and closer to the loop, the flux through the loop becomes larger. There's more and more flux, so to speak, because initially there will be not as much flux coming through the loop if the magnet is far away, and as you bring the magnet closer, since the magnetic field is stronger near the magnet, more and more flux lines will go through the loop. So where you can see that, first of all, the B field is through the loop like this, and the B field is increasing. So what you have to do in each case is determine the direction of the magnetic field through the loop, and whether or not that magnetic field is increasing or decreasing, which then causes the flux to increase or decrease. So we have a magnetic field pointing downward and an increasing flux through the loop. What that means is that an EMF will be induced, which will induce a current, which will be in such a direction that it sets up its own magnetic field to oppose the change. It's opposing the change. And this word is very important. It's opposing the change that caused the induced current. So, if it's increasing, it will set up a magnetic field that opposes the change, means it will set up a magnetic field in the opposite direction to try and keep it from increasing. So this is the B field that is induced, or the magnetic field that is induced by the induced current. Now you're ready to use your right-hand rule. If I point my thumb in the direction of the induced B field, or the induced magnetic field, and then I can curl my fingers in the direction of the induced current, that means that the induced current in this case will be in this direction. I induced. All right, if that didn't make a lot of sense, let's do a few more examples, and hopefully with repetition it'll start making a lot more sense. All right, here we have the situation. We have the magnet that went through the loop and is now moving farther and farther and farther away from the loop. The magnetic field will be in the direction towards the south end of the magnet. So the B field is in a downward direction. So the B field is in this direction. And then, since the magnet is going farther and farther away from the loop, the B field will be reducing, will be getting smaller. So increasing, we can call it decreasing. So the flux through the loop is decreasing, which means that, since it's changing, decreasing is a change, Faraday's law says that the EMF induced by the decreasing flux through the loop will cause an EMF, which will cause an induced current, which will set up its own magnetic field that opposes the change. So since the change is a decrease, the induced magnetic field will oppose the change, so we'll try to keep it from decreasing. So it will set up a magnetic field that's going in the same direction to try and prevent it from decreasing. So this will be the B induced. And now we use our right hand rule. Point our thumb in the direction of the magnetic field that's induced, and the fingers will curl in the direction of the induced current. So in this case, the induced current will be in this direction. So that will be I induced. All right, third example. Here we have a magnetic field caused by a magnet. South end is up, and the magnet is being pushed towards the loop, and the magnetic field direction will be downward because with a magnet, the magnetic field always goes towards the south end of the magnet. So the direction of the magnetic field that induces a current is downward. But since you're bringing the magnet close to the loop, so the closer you are to the magnet, the stronger the magnetic field, the flux is increasing. So we can have an increasing flux or an increasing magnetic field. Increasing, which means that the change in the flux, the increase in the flux, produces an EMF or induces an EMF, which induces a current which will set up its own magnetic field that opposes that change. So if the B field is in this direction and it's increasing, the magnetic field will try to prevent it from increasing, so it will set up a B field in the opposite direction to try and impose the increase. So this will be the direction of the induced, yep, there we go, induced B field or induced magnetic field. And now using my right hand rule, I point my thumb in the direction of the B field, and my fingers will curl in the direction of the current that's induced. So in this case, the induced current will be like this, I induced. Remember, the induced EMF will cause an induced current, which will set up its own magnetic field that opposes the change that caused it in the first place. So the change is an increasing magnetic field in the down direction. So to keep it from increasing, you'll oppose that increase by setting up a magnetic field in the opposite direction. So you kind of see the pattern. If the magnetic field is increasing, the induced magnetic field will be in the opposite direction of the increase. If it's decreasing, it'll be in the same direction because it's trying to prevent it from decreasing. Here it's increasing, the induced magnetic field will be in the opposite direction to try and keep it from increasing. And now let's look at our last example. Here we have magnetic field pointing towards the south, like this. So our magnetic field that causes the induced EMF is in an upward direction, and it is increasing because I'm bringing the magnet closer to the loop. And so since I'm bringing it closer to the loop, that means the magnetic field is increasing. The flux through the loop is increasing. So the induced EMF caused by the change in the flux through the loop will cause an induced current, which sets up its own magnetic field, which opposes the change, or opposes, in this case, the increase. So how do you oppose an increase? By going in the opposite direction. So this will be B induced. And then, using my right hand rule, I point my thumb in the direction of the induced B field. My fingers will curl in the direction of the current. And so this will be the direction of the induced current. I induced. I'm running out of room here. There we go. And that's how we determine the direction of the induced current by, again, we're looking at the direction of the magnetic field that causes the change in the flux. Then we figure out how the magnetic field is changing. Is it increasing or decreasing? If it's increasing, you're trying to prevent the increase, so you're going to have a magnetic field set up in the opposite direction. If it's decreasing, you're trying to prevent the decrease, so the induced current will set up a magnetic field in the same direction to try and prevent it from decreasing. And so Lenz's law, as you can see here, tells you or helps you figure out what the direction of the induced current will be. The EMF induced, Faraday's law will tell you what the amount of the induced current will be. Lenz's law will tell you what the direction of the induced current will be. All right, now we'll come up with some good examples so you can try to utilize this new information.